In the past, copper water pipes were commonly used as grounding electrodes because they provided a low resistance path to the earth. However, due to the increasing use of PEX, which is plastic pipe, for water supply lines, this is no longer recommended. PEX pipe is not conductive because it is made of a non-conductive material, therefore it cannot provide a path for electrical current to flow to the earth. Over time, copper water pipes can corrode, which reduces their conductivity, making them ineffective as grounding electrodes. If a copper water pipe is used as a grounding electrode and it becomes damaged, it could create an electrical hazard. A ground ring is required to ensure a reliable and effective grounding system, and there are several reasons why. Firstly, a ground ring creates multiple paths for electrical current to flow to the earth. This redundancy helps to ensure that the grounding system will remain effective, even if one or more of the paths becomes damaged. Secondly, the circular shape of a ground ring helps to minimize the resistance between the grounding system and the earth, ensuring that the grounding system can effectively dissipate electrical currents. Thirdly, a ground ring surrounds the entire building, providing uniform protection against electrical hazards. In cases where a copper water pipe cannot be used as a grounding electrode, there are alternative options. Firstly, ground rods are metal rods that are driven into the earth and provide a path for electrical current to flow to the earth. Secondly, ground plates are large metal plates that are buried in the earth and provide a path for electrical current to flow to the earth. Thirdly, concrete-encased electrodes are metal electrodes that are embedded in concrete footings or other underground structures. Regarding the specific question of why a 10-foot piece of bare 3/0 copper in a 2-foot trench cannot act as a grounding electrode, and why a ground ring is necessary, the reasons relate to the National Electrical Code, or NEC, requirements and the overall effectiveness of the grounding system. The NEC specifies requirements for grounding electrodes to ensure safety and proper function of electrical systems. These requirements are designed to minimize the risk of electrical shock, fire, and damage to equipment. The NEC favors ground rings and other approved grounding methods due to their superior performance compared to a short, straight length of buried copper wire. A ground ring electrode encircles the building or structure and is buried at a specific depth, typically 2.5 feet below the surface. This configuration provides a more extensive contact area with the earth, resulting in lower impedance and a more effective path for fault current to flow back to the source. The primary advantage of a ground ring is its ability to provide multiple parallel paths for fault current. This redundancy is crucial for ensuring that the grounding system remains effective, even if one section of the ring is compromised or encounters higher resistance due to soil conditions. The circular configuration also helps to equalize ground potential around the structure, reducing the risk of voltage differences that could cause equipment damage or pose a safety hazard to personnel. In contrast, a short, straight length of buried copper wire, such as the proposed 10-foot piece of 3/0 copper, does not offer the same level of performance or reliability. The limited contact area with the earth results in higher impedance, which can impede the flow of fault current. Additionally, a single straight wire provides only one path for current, making it more vulnerable to failure or increased resistance due to corrosion or poor soil conditions. The NEC specifies minimum lengths and installation requirements for grounding electrodes to ensure adequate performance. For example, ground rods must typically be at least 8 feet long and driven into the earth. These requirements are based on extensive testing and analysis to determine the optimal dimensions and configurations for effective grounding. Furthermore, the NEC emphasizes the importance of bonding all grounding electrodes together to create a unified grounding system. This bonding ensures that all electrodes are at the same potential, minimizing the risk of voltage differences and improving the overall effectiveness of the grounding system. In summary, while a 10-foot piece of bare 3/0 copper might provide some degree of grounding, it does not meet the NEC requirements for a grounding electrode. A ground ring, with its circular configuration, extensive contact area, and multiple parallel paths, provides a more reliable and effective grounding system. The NEC mandates ground rings and other approved grounding methods to ensure safety and proper function of electrical systems. Alternative grounding electrode options, as mentioned previously, include ground rods, ground plates, and concrete-encased electrodes. Ground rods are typically made of copper or copper-clad steel and must meet specific requirements outlined in the NEC. They should be at least 8 feet in length and have a minimum diameter, depending on the material used. Ground rods are driven into the earth, and their effectiveness depends on soil conditions. In areas with high soil resistivity, multiple ground rods may be required, spaced at least 6 feet apart, and bonded together to lower the overall grounding impedance. Ground plates, another alternative, are typically made of copper or other conductive materials and must have a minimum surface area as specified by the NEC. They are buried in the earth, and their effectiveness depends on the contact area with the soil. Like ground rods, ground plates may require multiple installations and bonding to achieve the desired grounding impedance, especially in areas with poor soil conductivity. Concrete-encased electrodes, also known as grounds, are installed within concrete foundations or footings. They consist of at least 20 feet of bare copper conductor, typically 4 American wire gauge or larger, encased in at least 2 inches of concrete. These electrodes provide a large contact area with the earth through the concrete and are generally very effective. The NEC specifies requirements for the installation of concrete-encased electrodes, including the minimum size of the conductor and the depth of the concrete encasement. The choice of grounding electrode depends on several factors, including soil conditions, local regulations, and the specific requirements of the electrical system. In some cases, a combination of different grounding electrodes may be used to achieve the desired grounding performance. It is essential to consult with a qualified electrical engineer or contractor to determine the most appropriate grounding solution for a particular application and to ensure compliance with all applicable codes and standards. Proper grounding is critical for electrical safety and equipment protection. A well-designed and properly installed grounding system can minimize the risk of electrical shock, reduce the likelihood of equipment damage, and improve the overall reliability of the electrical system. It is therefore essential to take grounding seriously and to follow all applicable codes and standards to ensure a safe and effective electrical installation. The NEC provides detailed guidance on grounding requirements, including electrode selection, installation methods, and bonding techniques. Adhering to these requirements is essential for ensuring the safety and reliability of electrical systems. In addition to the NEC, local codes and regulations may also have specific requirements for grounding. It is important to check with local authorities to ensure compliance with all applicable codes and regulations. Proper grounding is an essential aspect to electrical safety and should not be overlooked. Taking the time to design and install a grounding system that meets all applicable codes and standards is a worthwhile investment that can protect people and property from electrical hazards.